Welcome to today's Explainer. I am absolutely thrilled to guide you through this today because we're going to be stepping into the shoes of an architect. But, well, we aren't building with steel or concrete here. We're actually building with thermodynamics and equations. We're going to look at how to take a completely blank digital canvas and literally transform it into a fully functioning, highly complex digital chemical plant using Aspen HYSYS. If you've ever found yourself wondering how on earth engineers predict exactly what's going to happen inside miles of piping before a single wrench is even turned, well, you are definitely in the right place.
So here is our building block journey for today. First, we'll cover the Aspen HYSYS foundation, then moving fluids and thermodynamics. After that, heat exchange and separation. And finally, we'll wrap up with simulating chemical reactors.
All right, part 1, the Aspen HYSYS foundation, the digital rules.
To pull this off, we follow a pretty strict two-phase workflow. Phase 1 is all about setting up your simulation basis. Basically, this means you create your case, add your specific chemical components, things like methane, water, or nitrogen, and then you select your fluid package. Honestly, that last part, absolutely crucial. It dictates how all the fluid properties are going to be calculated. You literally cannot skip this. Only once that world is totally defined do you transition seamlessly into phase 2, which is where you enter the simulation environment and actually start building your flow sheet by adding material streams.
And here's something really cool. Aspen uses this brilliant visual feedback system. When you drop a pipe, or what they call a stream, onto your flow sheet, it starts out light blue, kind of just hungry for data. But once you feed it the core 4 variables, that's temperature, pressure, flow rate, and composition, it magically changes to this super satisfying royal blue. And that royal blue means it is completely solved.
Now, right behind that color change is a massive analytical powerhouse. HYSYS is basically taking complex equations of state, like the super versatile Peng-Robinson model, for instance, and translating them directly into tangible, real-world stream conditions in your workbook. It's like a giant calculator. You put in the heavy math, and it immediately returns practical properties, like calculated molar volumes.
Moving right along to part 2, moving fluids and thermodynamics. Thermodynamics in action.
So, when we're moving fluids around our plant, we generally use pumps for liquids and compressors or expanders for gases. Now, because these machines are, well, they're never 100% efficient, right? They generate wasted mechanical energy. The vital thermodynamic consequence of all that waste depends entirely on the specific equipment you're running.
Let's actually contrast a water pump operating with a kind of dismal 10% adiabatic efficiency against a gas compressor running at 30% efficiency. In both cases, the simulation reveals something super important. That wasted energy from the inefficient mechanical work, it doesn't just vanish into thin air. It transfers directly right into your fluid as heat. The pump shows an 18 degrees Celsius increase in outlet temperature just because it's inefficient, but because gases are highly compressible, the compressor's result is significantly more extreme. I mean, just look at the staggering number, 248 degrees Celsius. That is the temperature spike caused simply by compressing a natural gas mixture from 1 bar to 5 bar, with a low 30% efficiency. The final outlet temperature literally shoots up to 273 degrees. This right here shows exactly why simulation is so critical, because if you didn't anticipate that massive heat spike, you could absolutely melt your downstream piping. No joke.
Okay, now let's see what happens when we run that process in reverse using a gas expander. Here we're dropping the pressure from 20 bar down to 5 bar. Normally, expanding a gas cools it down, but again, efficiency is the name of the game here. Because our expander only has a 30% isentropic efficiency, that inefficiency actually fights against the cooling effect. We only achieve this really disappointing drop from 25 degrees down to negative 6 degrees Celsius. So, lower efficiency equals less cooling. It's just a fundamental thermodynamic truth laid bare by the simulation.
All right, on to part 3, heat exchange and separation, exchanging and splitting.
You know what I really love about modeling a heat exchanger in HYSYS? It's like a fantastic puzzle solver. Let's say we've got hot water at 250 degrees that we really need to cool down, and we're using cold water to do it. We know our target temperature, sure, but we have absolutely no idea how much cold water we actually need. Well, you don't have to guess. By just inputting your desired temperature targets and setting your pressure drops, Aspen HYSYS automatically calculates the missing piece for you. It tells us we need exactly 55.21 kilograms per hour of cold water to make the math work out perfectly. Now, what happens when we mix a bunch of things up and then need to separate them? Enter the flash separator. This brilliantly illustrates how the software handles multi-phase equilibrium. Imagine we're feeding 3 completely different streams into this vessel. We've got air at 70 degrees, steam at 400 degrees, and liquid water at 25 degrees. The exact moment you connect those pipes, HYSYS calculates all that chaotic mixing, finds the thermodynamic equilibrium, and instantly determines your final vapor and liquid outlet flow rates. It literally does the heavy lifting of phase separation in a fraction of a second.
But of course, true chemical plants don't just use simple flash drums, right? They use these massive, towering distillation columns to process huge volumes of material. Let's follow the sequential journey of natural gas through an NGL, or natural gas liquids, recovery plant. The whole goal here is to maximize valuable liquid recovery. The gas moves through 3 distinct phases. First, it goes into a demethanizer to strip out the lightest gas. Then, the bottoms flow right into a deethanizer. And finally, those bottoms flow into a depropanizer. It's this beautifully, highly orchestrated sequence.
And here is the real so what of this whole complex plant simulation. We aren't just moving fluids around for the fun of it. We're systematically separating heavier hydrocarbons to achieve very, very strict purity goals. For instance, in that very first column, the demethanizer, our primary goal is achieving a methane mole fraction of exactly 0.985 in the overhead product. Every single temperature, pressure, and flow rate in that entire tower is meticulously calibrated to hit that exact purity spec.
And finally, Part 4, Simulating Chemical Reactors, Digital Transformations.
So, HYSYS offers a few different ways to model a reaction, and the software actually scales its data requirements based on the complexity of the reactor type you end up choosing. If you go with a conversion reactor, well, you just need a base component and a known conversion percentage. Pretty simple. But if you step up to an equilibrium reactor, you have to precisely define the reaction stoichiometry. And if you go all the way up to a CSTR, that's a continuous stirred tank reactor, you've got to provide actual chemical kinetics, vessel volumes, and liquid levels. Let's take a quick look at each one.
Starting with the conversion reactor, which is just brilliantly straightforward. Let's say we have a stream of methane and a stream of air. To model this, you simply create a conversion reactor, group it into a reaction set, and attach it to your fluid package. Because you already know what percentage of your base component is going to react, you just plug in that known percentage, place the reactor on the flow sheet, and boom, HYSYS calculates the resulting heat and material balances instantly.
But wait, what if the reaction is reversible? You know, like the famous water-gas shift reaction used to increase hydrogen yield. Well, for an equilibrium reactor, precision is absolutely everything. You have to meticulously define your stoichiometric coefficients. Notice how reactants, like carbon monoxide and water, must be entered as negative numbers, while the products, like carbon dioxide and hydrogen, are positive. If you get those signs backward, well, your digital plant is just going to fail to solve.
Finally, let's dive into the intricacies of what I like to call the boss-level reactor, the CSTR. Here, we're trying to react propylene oxide with water to create propylene glycol. We can't just hand HYSYS a percentage here. No way. We actually have to combine the unifact property method to calculate unknown interactions, input specific Arrhenius parameters for the forward reaction, and even tell the software that our physical vessel is exactly 280 cubic feet and running at an 85% liquid level. We're literally simulating real-world kinetic constraints.
And after inputting all of that highly complex kinetic and spatial data, we hit Run, and the software reveals the really exciting bottom line of our CSTR simulation. With an initial isothermal temperature of 75 degrees Fahrenheit, we successfully achieve a 40.3% conversion of propylene oxide to propylene glycol.
So from a completely blank screen to a beautifully royal blue glowing flow sheet, we've used these digital building blocks to predict temperature spikes, solve heat exchangers, and simulate some pretty complex chemical kinetics. So my final question for you today is this. When you sit down to architect your own process simulation, what invisible thermodynamic insights will your digital plant uncover? Thank you so much for joining me on this explainer, and hey, happy simulating!